do we got to do to make it an
pH of 4 to 5.
pH of 4 to 5 with what? Ketone, that's or aldehyde. What's the other ingredient? Primary amine or ammonia. Well, let's see. Here we have an imine. Here we have an aldehyde. And a primary amine. They just happen to be in the same molecule. The oxygen came from water. Now, once again, when we went through the mechanism of imine formation, I told you it's reversible. The reverse is called hydrolysis. This is nothing more than the hydrolysis of an imine. It's the reverse of the mechanism that we work through in the forward direction. So once again, when you have a reversible reaction, the mechanism is reversible. It's important that you're able to think about the mechanism in both directions, because there's always, on this test, a mechanism where, if you thought about what I always say, you might want to think about this on your own, but there's always a question where it's going to be the hydrolysis of something that we talked about, but we never went through the mechanism. I'm going to do you a favor and go through the mechanism of imine hydrolysis. I'm not going to do any other hydrolysis tonight. Enamines can be hydrolyzed when you expose them to aqueous acid. That's when we've got, the secondary amine reacting with an aldehyde or a ketone. We've got the carbon double bond. Acetals can be hydrolyzed. Did an acetal hydrolysis actually in homework 5. Okay. So this is just an imine hydrolysis. We're running the mechanism of the formation in reverse. Well, get our double bond in there. If you go back and you look at your notes or look at what I posted in Canvas, that was a pretty meaty mechanism. I think that took a whole page. The last step in the mechanism of imine formation was we pulled a proton off of nitrogen. We had a protonated aminium ion, which was resonance stabilized. Well, another pattern that is really going to become evident, probably not until, even after exam 3, because amines are one of the last functional groups that we talk about. When you have nitrogen, which is an even stronger base than oxygen, nitrogen is a better base than oxygen because it's less electronegative than oxygen. It's a little bit more willing to give its lone pair away and grab a proton for that reason. So, if oxygen-containing organic molecules get protonated when you expose them to strong acid, you're sure as hell going to protonate the nitrogen atom of this nitrogen-containing organic molecule. The patterns repeat themselves in organic chemistry. And again, recognizing kind of acid-base and relative acid-base strength, that goes all the way back to Organic 1. That goes back to chapter 4 in this textbook. Really, it goes back to General Chemistry 2. So we're going to end up protonating that nitrogen. And what do you know? We have, and of course we're going to end up producing water as the other product of that acid-base reaction. Well, one of the reasons why it's so easy to protonate the nitrogen atom with an imine is because when you protonate that nitrogen, this is the real structure. Now, if this were the question where you're supposed to draw all of the important resonance structures, then you've got to be able to do that. So let me again just remind you, the pattern is when you have a positively charged atom that's directly involved in a pi bond, move the pi electrons onto that atom as a lone pair, you end up getting another resonance structure. Nitrogen is still part of that ring. It still has a hydrogen. It now has, I'll put the lone pair out there where it's a little bit easier to see. Positive charge is there. This is a resonance stabilized cation. These patterns always repeat themselves. Maybe I got a little OCD. Maybe I love organic chemistry so much because I love patterns. Who knows? But when you start to see the patterns, you start to see that all of these different reactions really aren't so different. And then you start to see kind of the beauty of it, especially when we start to kind of put these mechanisms together, and that's really what starts to happen in chapter 19. So by protonating that nitrogen, we have made the carbon that's attached to that nitrogen a much more powerful electrophile. So it's going to be very attracted to that water. Again, let me just emphasize, we are working under acidic conditions. When we made the enene, when we made the enene, the pH was somewhere between 4 and 5. Now, usually on a test, I'll just write pH equals 5, just to make it a little bit simpler. But acidic conditions, you're going to have cationic intermediates. So cation, this is a resonance stabilized cation. When this oxygen comes in, we're going to end up having a positive charge on that new oxygen that's now incorporated into this molecule. And then we're going to deprotonate, I should say. Again, when we're in aqueous acid, H3O plus is the proton donor, water is the best proton acceptor. There's something called the leveling effect that says the strongest acid that can exist in a solvent is the conjugate acid of the solvent itself. And water, the strongest acid, is going to be hydronium. Any stronger acid than hydronium reacts with water, makes hydronium. That's why we typically just use H3O+, at least I do, in these mechanisms when it's aqueous acid. So now we've got our carbonyl amine is what it boils down to. So there's that ethyl group, close off the rest of the 6-member ring. OH, H3O+. So this is the carbonyl amine. This is basically what we got as the addition product when we reacted an aldehyde with a ketone with a primary amine. Secondary amine does the same thing. In going towards the imine or the enamine, what happened was we protonated, we're running that movie backwards. I really want you to go back, look at your notes, look what I posted in Canvas, and recognize that we are basically running the steps for that imine formation mechanism. Different molecule, the same mechanism, in reverse. So where do you think we're going to react the acid next? It's got two choices. It's either going to go to the oxygen or it's going to go to the nitrogen. It's going to go to one of the atoms in this molecule that's got a lone pair. Got to be the nitrogen, because if we go to the oxygen, it's just taking us back in the direction from which we just came. So these are reversible reactions. So, that certainly happened. That's certainly happening. There's plenty of these carbonyl molecules that when they form, you just reprotonate the oxygen again and it goes back, takes you back to the amine. But every once in a while, and in this case, it's even more favorable because nitrogen is a stronger base, you are going to have that nitrogen pick up a proton. So now it's going to have two hydrogens. It's going to have a positive formal charge. There's our ethyl group. We still have a hydroxyl. And now we've set this up to depart as a leaving group. What I'm going to do is I'm just going to take this directly to the relatively more important resonance structure of the next species. Now let me draw this kind of in a way so it looks like what I'm basically trying to draw this in the same orientation. So that nitrogen picked up a lone pair. And then we've got a CH2, 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 double bond. Did not draw my water in that previous proton transfer. This is a resonance hybrid. This is just a protonated aldehyde. Now, there is a hydrogen on this carbon, it's just not drawn. There was a hydrogen on it in the original structure, it's just not drawn by angle convention. Well, to get to the final product, all we've got to do is pull off that extra proton on that carbonyl oxygen. Here's our NH2, let's see, CH2, 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 C double bond O, H3O plus. Sometimes you'll see aldehydes drawn without explicitly showing the aldehydic hydrogen, but I like to draw it in. That's our final product. Compare this mechanism side by side to the imine formation. You will see it is exactly the reverse. All the reversible mechanisms we talked about, you can do this with. And again, it's important to do that. Hopefully you did a pretty good job with maybe you didn't recognize it was an acetal hydrolysis. One of the mechanisms on homework 5 was definitely an acetal hydrolysis. You've got to recognize these patterns, and again, they always repeat themselves. So 4 pages of mechanisms on the test. As I said, that first page kind of getting you warmed up. It's just 4 reactions. You are going to tell me what happened, and then you're basically going to show me the arrow pushing for the first step in the mechanism. There's something that's basically the reverse of a mechanism that we talked about. As I said, there's a reaction that you've never seen before. There's a reaction that we've seen, but maybe didn't cover the mechanism in detail. Again, all the patterns repeat themselves. I'll tell you that one of the mechanisms is in acid, one of them is in base. The one that's in acid, cationic intermediates, you're going to have a lot of resonance. In base, anions tends to be a little bit more straightforward. Okay. Let's talk about some synthesis. And the first one that I want to talk about is at the request of Alicia. I'm not around on campus very much, so Friday she texted me and said, you've got to talk about this problem during the review session. So the way that I will typically, now, again, there's only 2 pages of synthesis, and I'll kind of map that out for you. One of the pages, I basically, given you the synthesis, I give you the scheme at least. You're going to be filling in the empty boxes in the scheme. Again, that's kind of the warm-up. And then there's only 2, so I think that's actually a little bit less than on the old test that I posted. There might have been 4 on that test. But there's 2 problems that are kind of like this, and there's a box at the top of the page, that kind of outlines the rules. You are always preparing the target. So we are trying to prepare this, so that will be listed as the target. And I point this out because there's always, every semester, at least a few people that don't read the directions. And they start with the target and then try to break it apart to get the precursors. And that's not answering the question that was being asked. So you're preparing the target from these, it might be 2 or 3 things as the only sources of carbon atoms in the target. So the idea is, and this is going to become even more important on the next test because a lot of the Chapter 19 chemistry focuses on carbon-carbon bond-forming reactions where we can actually put together 2 reasonably complicated things in one fell swoop. So those condensation reactions that we're going to talk about in Chapter 19 are really perhaps the most important synthetic reactions of the semester. And that's why, as I said, probably test 3, the emphasis will be flipped, more synthesis, less mechanism on test 3. Okay. But the strategy is, and this only becomes more important, you've got to kind of look at the target. You've got to try to identify where the starting materials are showing up in that target. And then it's really important, and this becomes even more important, you've got to think backwards. It's not always obvious to, what reactions do I do on these precursors to get to the target. That's not the way organic chemists think. If we're trying to make a target, we look at the target, we try to think about how we can get that as the major product in a single transformation. And then we progressively work our way back to the starting materials. Now, sophomore organic chemistry, it's contrived. In the real world, we work our way back to starting materials that are readily available and hopefully not very expensive. And why do we do this? Because in the real world, if you're trying to make, Taxol, very potent drug that's very effective for certain types of breast cancer, to get the amount that would cure one woman with breast cancer, you would have to cause the Pacific yew tree to be extinct. A lot of the compounds that we make are present in nature, but not in significant abundance. We try to come up with ways of making in the laboratory what Mother Nature makes, out in the real world. Okay, so we got to try to find our fragments. Well, we've got a 1, 2, 3, 4, 5 carbon fragment and a 2 carbon fragment. 1, 2, 3, 4, 5, 6, 7 carbons in the target. Well, fortunately, 5 plus 2 equals 7. And given the symmetry in that target, it really doesn't matter where I identify the new carbon-carbon bond. Let's see, it's probably going to be there because that's kind of resembling these circle things. This fragment maybe came from here, and that would mean the other piece, methyl, that probably came from here. Okay. Now for this one, I'll do the retrosynthesis in a minute. I just want to kind of show you what bothered Alicia so much. Most people recognized that there was going to be a Grignard reaction during the course of the mechanism. How do we make Grignard reagents? We expose organohalogens to magnesium ether or THF salt. What's the problem with that reaction? It's wrong, but why? The reason why I'm mentioning this is because Alicia said that most people did. I actually have not even gone in. I haven't had time to look at the scores for 1.5, and I'll get that extra credit posted. I'll probably just go in and do all the grade stuff once the exams are graded. But the vast majority of people who attempted that problem on homework did this, and it's flat out complete utter BS. It's not going to work. Because you have got to remember that Grignards are going to react with carbonyl compounds. If you've already got a carbonyl compound in the substance that you're trying to turn into a Grignard reagent, that's not compatible. You're not going to be able to make this Grignard and then expect that it's just going to wait around until you add the aldehyde that you want it to react with. That's not the way molecules work. There are varying things, there are various functionalities that are incompatible with those organometallic reagents. That goes back to test 1. This is even a test 1 reaction, really, but it's so important for aldehyde ketone chemistry, but it's certainly going to show up on this test. You can't do it because you're not going to be able to prevent the Grignard that you just made. It might do an intramolecular reaction, or you might get some polymerization taking place. It's not going to wait around until you throw in the other aldehyde. So the point is, you often, when you have incompatible functionality, have to come up with a way of disguising that incompatible functionality so you can do the transformation that you want to do. And we talked about how we can do that when we had an aldehyde or a ketone that might interfere with some other